Here we start with the new section, fluid mechanics. Now, fluid mechanics is divided into three or four parts. The first part that we are going to understand is hydrostatics, along with the concept of atmospheric pressure. Uh, Secondly, surface tension and viscosity. Now, at first, we try to understand what do we mean by a fluid, FLUID, fluid. What is a fluid? We all know liquids and gases do not have any definite shape of their own, and they can change their shapes easily, as these substances are not very rigid, they are not very hard, they do not have the capability to restore their original shape. We all know that if we pour water into a vessel, it takes the shape of the vessel. Now, for this reason, the liquids and gases at rest cannot resist the tangential force acting on them. Liquids and gases at rest. Now, this part at rest is very important. Liquids and gases at rest cannot resist the tangential force acting on them. Now, this is the reason why liquid flows from one vessel to another, liquid or other fluid flows from one vessel to another. When we try to pour the liquid into another vessel, we are actually introducing the tangential force. So we have written that the liquids and gases, combined term is fluid, at rest cannot resist the tangential force acting on them. And due to the application of even a slight tangential force, this substances begins to flow. As these substances can flow, so the name fluid comes. Now, the first thing that I have written here is hydrostatics. Now, what does this term hydrostatic mean? It is a branch of physics in which we are dealing with all these kinds of fluids, liquids and gases. Now, what we can write, the branch of physics in which the characteristic properties of fluids. Hydrostatic means the properties or the characteristic properties of fluids at rest are studied is called hydrostatics. So, what is hydrostatics? It is a branch of physics. In short, we can say it is the study of fluids at rest or the properties of fluids at rest. Properties of fluids at rest. Two components of fluid, liquid and gases. For liquid, we can say that it has got a definite volume but no definite shape. It takes the shape of the container in which it is kept. But for gases, we can say that gases neither have a definite shape nor a volume. They do not have a definite shape nor volume of their own. They usually take the shape and the volume of the container. Consequently, a gas can be compressed easily. The compression of a gas can be done very easily, whereas liquid is almost incompressible. Gases can be compressed, whereas liquids are almost incompressible. Now, one or two terms, you already know these terms, you know the definition of these terms, but for this chapter, we have to go through these things. I am going through these things very quickly. Density, we all know that is mass per unit volume. The SI unit of the density is mass is in kg and volume is in cubic meter. The CGS unit will be gram per centimeter cube. Dimension of density is equal to ml to the power minus 3. Now, one thing, if you have passed class 10, one thing you people all do is the mistake for converting SI to CGS or CGS to SI. Now, suppose density of a liquid or density of a solid is suppose 3 gram per cc cubic centimeter in CGS. We want to find the value in the SI system. We want to find the value of the density in the SI system. 3 into, it must be 1000. It is 3000 kg per cubic meter, but you all do the opposite of this. The value of density in CGS has to be multiplied with 1000 to get it to the SI system, or kg per cubic meter. Now another term is specific gravity. Another term is specific gravity. The term specific gravity means this is the density of a substance with respect to another substance. It is something of a type of a ratio. Specific gravity is the ratio of two densities: density of the substance by density of water, at 4 degrees centigrade. Now you all know why do we take the water to be at 4 degrees centigrade, because we all know the density of water is the maximum at 4 degrees centigrade. So this is the ratio of two densities, hence it has got no unit. But these are the things you have already studied in class 10. One thing you have to learn here is comparison of density and specific gravity in terms of magnitude. Comparison of density and specific gravity in terms of magnitude. Now what happens if you have to find the density of the substance? From this formula we can say the density of substance is specific gravity of the substance into density of water at 4 degrees centigrade. But in the laboratory it is very difficult to find water at 4 degrees centigrade, to get water at 4 degrees centigrade. So there must be a temperature correction of specific gravity. This is a new thing you have to learn here. Temperature correction of specific gravity. Now how to do this temperature correction? We denote specific gravity by S. We know the volume of this density of substance by density of water at suppose T degree centigrade, because the room temperature in the laboratory can be around about 22, 25, 28. So we have water at 28 degrees centigrade in the laboratory. So we divide the density of water at that temperature only. And another term, density of water at T degree centigrade by density of water at 4 degrees centigrade. Now this is somewhat of a mathematical calculation. Like this we can write A by B is equal to A by C into C by B, multiplying C in the numerator and denominator. This is the type of calculation done here. Density of water at T degree centigrade has been multiplied in the numerator and denominator. Now it is very easy to find this one, density of substance by density of water at T degree centigrade. And this is the density or the specific gravity of water. Now density of water at T degree centigrade, 20 degrees centigrade, 40 degrees centigrade, by density of water at 4 degrees centigrade means this is by definition the specific gravity of water at T degree centigrade. Now this specific gravity of water at T degree centigrade can be found out from a chart which we get in the laboratory. So this part we can calculate by mathematical calculation, and this is the part we have to obtain from the chart in the laboratory, from which we can get the density or the specific gravity, or rather the specific gravity of water at T degree centigrade. So by definition we can write S is the specific gravity of substance, this fraction, into specific gravity of water at T degree centigrade, this fraction. Now pressure, we all know pressure is equal to force per unit area. Pressure, therefore force is equal to pressure into area. The dimension of pressure is equal to m L minus 1 T minus 2, dimension of force by dimension of area. Now for pressure we always write, for F we write the term as thrust and not as force. Thrust by area. uh, dimension of thrust is same as that of force. So the term thrust means force. Now what happens when a liquid column is taken? This is a can which you can fill up with a liquid. This is the free surface. Depth of h, a p point is taken, what or rather a point is taken. What is the pressure at this point A? From the free surface, the depth is h. What is the amount of pressure acting here at this point A? So pressure at A, for this we have to consider a liquid column or a cylindrical column like this. Now the cylindrical column has a base area of base area. Suppose A, we name this point as rather C or not A. Base area A. Now the weight of liquid column is equal to, now we know weight is equal to mg. Now what is m? V into d into g, or rather rho into g you can write also, v into d into g. So volume into density of the liquid column into g. Now what is volume? The area of cross section is a here and the height is h, so h into a, so h into a by dg. So this is the thrust, weight or rather the thrust applied on the base area A. So the pressure at this point, pressure at point C must be equal to, we know the from definition, force by area or thrust by area. So H A dg by area A. So A gets cancelled, the formula comes as H dg. In many books you can find the density written as rho and not d. Now we had already taken the point B at C. So the pressure at point C we have found out to be HdG, but actually the pressure at point C is not HdG. This is the pressure due to the liquid column. This is the pressure due to liquid column from this point to this point. So the total pressure acting on point C, total pressure at point C must be equal to PC, or the rather H rho g plus PA. Now what is PA? PA is the atmospheric pressure acting on the top surface of the liquid. So the pressure or the total pressure acting here is H rho g plus the atmospheric pressure acting on the free surface. So this is the sum of two pressures. The lower classes in class 9, 10 we know the value of PA, it comes out to be 1.013 into 10 to the power 6 dyne per centimeter square. Now how to convert dyne per centimeter square into Newton per meter square? If I can correctly remember, that is 1 Newton per meter square must be equal to 10 dyne per centimeter square. So 1.013 into 10 to the power 5 Newton per meter square or Pascal. So the unit of pressure is Newton per meter square or Pascal. Now here are some points about the liquid pressure. You all know about these points. You studied in class 10 or 9. I have jotted some points here. Number 1 is pressure increases with depth. That means the formula was H dg. As H increases, that means the depth increases, the pressure increases. Number 2, liquid exerts pressure at a point inside it equally in all directions. From a particular point, the pressure exerted by the liquid in all directions. All directions means in 3-dimensional frame. The pressure at a point inside is all equal. Now point number 3, the pressure exerted at different points on the same horizontal plane inside it is same. So if this is the horizontal plane, the pressure exerted at this point and this point and this point will all be of the same value. Now the action of a small hole made on the wall of a container. So this is the small hole made in the wall of the container. This container is filled with liquid, water say. So the lateral pressure acting at this point on the hole, the lateral pressure, or rather the The lateral pressure acting on this hole is the depth suppose it to be h, so h dg is the lateral pressure. Now what happens, the liquid tries to flow out of this hole like this. The liquid flows out in this fashion. Now as the level of liquid falls because the water is moving out of the hole, as this top layer recedes downwards, the velocity of flow also gets reduced. Due to this lateral pressure, the liquid comes out through the hole. Naturally, with the ejection of the water or the liquid through the hole, the level of water goes down in the container, and hence the lateral pressure exerted by the liquid gradually decreases. Now, this is the reason for the rate of flow through the liquid through the hole also decreases gradually. So, the rate decreases as time passes by. Now, how to find the velocity of efflux? Now, the velocity with which this liquid moves out of the hole is known as the velocity of efflux. Velocity of efflux, EFFLUX. Now, how to find this? We can say that the work done in ejecting the liquid through the tube. We can write work done in ejecting liquid through tube. Now, how do we find the work done? This is by the applied force into the displacement of liquid, displacement of liquid. Now, what is the applied force? We can write, instead of applied force, we can write pressure into area. Applied force is pressure into area into displacement of liquid. Displacement of liquid. Now, pressure exerted on the hole, or rather the pressure or pressure exerted on the hole rather. Now, area into displacement becomes the volume. So, pressure on hole into the volume of ejected liquid. Area into displacement, meter square into meter. So, meter cube becomes the volume of the ejected liquid. Now, work done in ejecting a liquid of unit volume is equal to the pressure applied on the hole. So, if we take work done by volume, if we take volume onto the left hand side, becomes equal to the pressure on hole. Now, work is converted into kinetic energy per unit volume of the liquid because the water is moving out with a speed. So this work gets converted into the potential energy, the kinetic energy rather. Now, if the density is rho and the velocity is v, the mass per unit volume of the liquid and the kinetic energy is half rho into v square. So it becomes half rho into v square because rho means mass per unit volume. This is per unit volume. Work is, you can write here, half mv square. mv square is the work done by volume capital V. So m by v becomes rho or density into v square. So half rho v square is equal to h dg. From this we get v square is equal to 2gh, or rather v is equal to square root of 2gh. Now, equilibrium of two different liquids in a U-tube. Now, this is a very important topic. Questions for joint entrance and all these things comes from this part. Now, what do you mean by equilibrium of two liquids, two different liquids? Now, suppose if we pour one type of liquid into the vessel, the liquid will settle downwards, and suppose the initial marking of the liquid will be like this. So this is one type of liquid. Now, if we pour a second type of liquid through any one of the limbs, now one thing I must have mentioned, that is the cross section of the tubes must be the same. The cross section of the tubes must be same. We will also discuss problems in which the cross section of the tubes are not same. What happens in those cases? We'll discuss it later. First is the cross sections are same. We have poured one liquid. The liquid settles like this. The level in both the tubes or the limbs of the tube are same. If we pour a second liquid into this or into this part will go downwards and this part will be raised upwards, because the pressure or the weight of the liquid or the second liquid that I have poured into the first limb will pressurize the first liquid to move downwards. So this will be the resulting position of the liquid. So this and this will be the final position. This will be one type of liquid. This will be one type of liquid. Suppose it's liquid 1, and the rest will be the different type of liquid. Now, how to solve these problems is very simple. The last level that we can see here is this one. The last level or the lowermost level that we can see here is this one. We will be drawing a imaginary line like this. Now this point you can name it as point number C, point C, and this point as point D. Now as these points are at the same height from the ground level, so the pressure will be the same here. So pressure at C must be equal to pressure at D. This is what is known as the equilibrium of the two liquids. So in equilibrium we have already studied, at the same horizontal level CD, the liquid pressure at point C must be equal to the liquid pressure at point D. Now how to find these things? If we can take the height of the first liquid in the first column, suppose it to be H1, the density as D1, that means H1 D1 into G must be equal to this height is H2. This is comprised of another liquid. Suppose the density is D2 and G. So height H1 is of the first liquid and the height H2 is of the second liquid above the point D. So G gets cancelled out. So H1 by H2 becomes D2 by D1, density 2 by density 1. Now we take a very simple example of the previous theory. This is a vertical U-tube of uniform cross section. That means the cross section of both the limbs are same, which contains mercury. So the mercury level in both the tubes would be like this at the beginning or at the initial stage. Now through one of these limbs, some water is poured such that the mercury level in that limb goes down by 2 cm. So the liquid here that is poured into the first limb is water such that the level of mercury goes down by 2 centimeters. So the liquid level or the mercury level in the second limb also rises by 2 centimeter, because the condition has been stated that both the area of cross section of both the limbs are same. Now the height raised by the mercury in this tube is 2 centimeters. The liquid column that has or the mercury column that has fallen down a distance of 2 centimeters. Now they have asked what will be the height of the water column. What will be the height of water column? Now as I have stated in the theory, we can mark the liquids like this. This is mercury, the green dots are mercury and the pink dots are that of water up to this level. Now the condition has been given that the water level falls down through a distance of 2 centimeters, the mercury level falls down through a distance of 2 centimeters in the first limb. So This is 2 centimeter, this is 2 centimeter. We draw an imaginary line from the last line that we have found out. By geometry, this has also to be 2 centimeters. This distance must also be 2 centimeters. So if we can name these points, or rather if we don't name these points, this is point number C, this is point D. So from equilibrium we have already learned PC must be equal to PD. Now PC is equal to, if we take this to be x, so x plus 2 is the height of the water column, into the density of water is 1 into G. Similar for the case of mercury, the height is 4 centimeter, density of mercury is 13.6 into G. G gets cancelled out, x plus 2 is equal to 54.5. 6 for 24, 2, 12, 14, 1, 5. So x is equal to 54.4 minus 2, that is 52.2. So the height of water column was x plus 2. So the answer will be 54.2 centimeter. Now another problem in which the cross sections are not same. So let us first try to draw the diagram in which the two limbs are not same. So this is one limb which is thicker of the two. So one limb has an area of cross section of 3 centimeters square and one has an area of cross section of 1 centimeter square. Now the 60 cubic centimeter of water is poured into the wider limb. Now first, I think I have missed out a point. Some mercury has been poured. Some mercury has been poured. Some mercury has been poured. So the mercury column at first was suppose like this. Now 60 cubic centimeter water is poured into the wider limb. So 60 cubic centimeter water has been poured. So the length of water column is equal to 60 centimeter by 3. 3 was the area of cross section of the, so 20 centimeter was the length of the liquid column poured. So when the water was poured, the initial level of the mercury will fall downwards. Suppose it falls down through a distance of x. Suppose the mercury level, or the initial mercury level falls down through a distance of x. So there will be a surge in the liquid level in the second limb, but as the limb is thinner here, so the liquid level will rise here by distance of 3x, because this is 3 times less, the area of cross section is 3 times less than that of the thicker limb. So if the liquid level falls by distance x in this, the rise in the liquid level in the second limb will be 3x. Now if we take the same concept, draw the imaginary line like this. By geometrical consideration, if this distance is x, by geometry this will also be x. So we take this point to be D, we take this point to be rather C. So equilibrium means again PC is equal to PD. So this part was water. This part was water. And the rest part, this portion was mercury. So PC is equal to PD means the height of the liquid column was 20 into 1 into G, because the height of the water column was from this to this point. So this length we have found out already to be 20. So 20 into density of water 1 into G is equal to 3x plus x into 13.6 into G. Now from this, if you calculate this from this equation, the value of x, we get it to be 0.368 centimeter. So the mercury column, the rise in mercury column equal to 3x. The rise in the market column is 3x. So 3 into 0.368, that is 1.1 centimeter in the narrower limb. Now lateral thrust on a body. Now suppose this is a tank. This is the body. We name the body as A, B, C, D. Suppose AB is at a height of h and CD is at a height of h plus b. That means BC is equal to b. The side BC is equal to small b. So the depth of AB equal to h, and depth of CD is equal to h plus b. Now we find the average pressure on the surface ABCD. Average pressure on ABCD, that is H rho G or H dg, you can write also, density as rho or density as G. H plus B into rho G by 2. So it becomes H plus B by 2 rho G. So the lateral thrust must be equal to the pressure into area. Now what was the pressure expression? H plus B by 2 rho into G. And what is the area? A into B. That means we take AB as A, the distance AB as A, and BC as B. So the area of ABCD, the figure ABCD is AB. So this is the expression for lateral thrust.